that science is from the humans that animate or pursue it. Let's just take a moment to consider the current situation, the elephant in the room, which is, of course, that we are having a global pandemic. So I want to acknowledge that, and different people are being affected in different ways. So let's keep that in mind. And in general, in that spirit, I want to also mention, right, we are three-dimensional beings. It's just not kind of brainless or disembodied brains that walk around doing astrophysics and physics. And so in that context, I will introduce my group. So Marc Williamson, who's a graduate student, Tyler Pritchard, who is a postdoc in my group, and Janelle Sai, who's also a graduate student in my group. So today we'll do kind of a tag team of for Supernova Explosion. So I'll do kind of give a broad introduction, since we have different backgrounds in, CCPP. And then Marc will do the deep dive on his research project on specific kinds of explosions. And so general, also I was thinking it would be nice to start brown bags with just kind of personal information people want to share. So hobby. So my hobby is my 4-year-old. He's very rambunctious sometimes, and science fiction movies. So I always look for good suggestions. I include them in my teaching too, because that's something that a lot of people also have access to, especially our undergraduates who the other things I do is I'm a faculty fellow in residence. So I live in the residence halls. I live in the Brooklyn Halls residence halls with the undergraduates. So it's been a really interesting way to get kind of insight into our graduate students, undergraduate students, the research they're out there, and what's happening on the ground. And I think that improved my teaching, has made me, I think, more compassionate and more understanding. And the resources that are out there at NYU, so actually NYU cares. Especially, in terms of the resources, there are a number of resources out there. So if you have any questions in general about research, teaching, life stuff, related anything, as we say here, we can't really always separate science from the people. So I'm happy to be a resource. Okay, so now let's talk about supernovae. So first of all, why they're important, why should we care, right? With any kind of talk, you want to start with that, especially if you have a broad audience. So supernovae are important for many things. So one, they're cosmic engines. So they produce a huge amount of energy that gets released during the explosion. So remind ourselves, supernovae, first of all, are explosions of stars. And basically, there are two kinds of explosions. There are the explosions of massive stars. So when we talk about massive stars in astronomy, we refer to stars that are more massive than 8 solar masses, because above 8 solar masses or so, the lives and deaths of stars become very different compared to the low mass stars, like our sun. The other types of explosions are explosions of carbon-oxygen white dwarfs. So of course, our sun will become a white dwarf. It will become a carbon-oxygen white dwarf at the end of its life, but it will not explode because it doesn't have a companion. It doesn't have a binary companion. It turns out stars are very much more social than our own sun. There are lots of binaries and triplets out there, but not in our sun's side. So these are the kinds of explosion stars. And both of them, turns out, because of various reasons, coincidentally, they produce similar amounts of kinetic energy when they explode. So that's around the kind of 10 to the 15 wonders that has been quoted. These days, we have like ±1, because there are these very energetic explosions, 10 to 52 Earths, that are connected with gamma ray bursts, which are another kind of, very extreme explosion that Andrew McFadden and his group is studying. So these are cosmic engines. That's a lot of energy. That's around 10 to the 28 megatons of TNT. So these are very, very powerful explosions. They drive galaxy evolution. When people talk about, in your kind of cosmological simulations, your friends, colleagues who are doing that, when they talk about stellar feedback, that's what they're referring to. It's kind of the death of the star. Some massive stars also have a lot of feedback during their lives, but mostly these kinds of explosions give most of the feedback or the kind of kinetic input. kinetic energy input. So both types produce heavy elements, right? So heavy elements. So cosmic engines, heavy element input, heavy elements. So of course, Big Bang nucleosynthesis only produced a few of the elements that we have, hydrogen, helium, a little bit of lithium. So the lithium battery of your laptop is primordial lithium. And of course, there's a big lithium problem in the field that's very interesting. But everything else was produced inside stars, massive stars, as well as low mass stars. For example, carbon gets produced in low mass stars. And then ejected during the explosion, as well as synthesized. And another field that has gained a lot of traction or interest is, of course, transients in general. So these are referring to objects that change over time, right? If you think about astronomy, you usually think of like things that are on billion-year timescales, but there's a very emerging field where things change in a matter of seconds, minutes, days, or years, which is kind of much more of a human time scale that we're now starting to observe while making movies of the sky, like the upcoming LSST survey under the Rubin telescope in Chile. And so in terms of transients, there's a new kind of transient on the field, or kind of on, in the club, called the kilonova. So not a supernova. So nova, of course, comes from Latin. I took actually Latin in Germany in high school. Latin in nova means new, of course, new star. And historically, when people over the last 2,000 years on Earth observed these kind of explosions, they saw them as new stars that then faded. So in Chinese, actually, they're called guest stars. So these were explosions that would become very luminous and then would fade. And ironically, of course, then these are not new stars, even though they're called supernova, they're old stars. They're exploding. But of course, they couldn't see the progenitors. For them, it looked like it was a new star. So kilonova are interesting because they are produced during the merger of two neutron stars that LIGO observed in 2017, for which the Nobel Prize was awarded. And of course, the gravitational field astronomy has really kind of exploded. Since then, LIGO is producing lots of detections, not of neutron star mergers, but of black hole mergers. And so that's kind of an area of nucleosynthesis that's been interesting for what's called odd process elements. I won't discuss them in detail, but that's a really very fascinating field. It includes gold, uranium, all these other kind of important elements. And we think they might be produced in these neutron star mergers. So these are sources of heavy elements, and of course, beacons. So they're very luminous. So this is the kinetic energy that I showed here. But of course, these explosions can be between 10 to the 8 to 10 to the 10 solar luminosity. So this is the symbol for the sun, the circle with a dot in the center. So these are similar to galaxy luminosities. So they have similar luminosity and not outshine their galaxies. So they're really big beacons. That's what type 1A. So these are the 1A supernova from white dwarfs. And some kind of binary system has been used to discover the acceleration of the universe. Right? It was the Nobel Prize that was awarded 2011 for the two competing groups that made the discovery in '98. So I was an undergraduate when it happened in that group. So it's very exciting. So they are strong beacons, can be seen over cosmological distances. So this is in spatial cosmology, as well as in connection with gamma ray bursts. So gamma ray bursts are brief explosions or brief flashes of gamma rays from specific kinds of stars exploding. And they can be seen up to redshift of 10, which is when the universe was only kind of 500 or so million years old. So these supernova Grbs, and particularly Grbs, can be used as beacons of cosmological distances to look at star formation histories and so forth. So all of it as well, you might ask, like, okay, so that's a very broad background. So what about kind of the specific things we're doing? So what we're doing in my group, one aspect is looking at spectra. So one aspect is looking at spectra. So as if, light as a function of wavelengths. Spectra are very important because they tell us about the composition of the explosion. So let me talk a little bit about the different subtypes. That's going to be important for when Marc will discuss a specific subtype. So spectra. So from then we can get supernova subtypes. That's how we used to identify and classify them. But of course, you might ask, what are the kind of outstanding questions in the field? So for the different subtypes, and I'll discuss in a second, but basically for all of them, including the carbon-oxygen white dwarf in some kind of binary system, which is a type 1a, and massive star explosions, the big question we have is, how are the subtypes related to their stars? Because we see the stars before they explode, or Milky Way, for example, or nearby galaxies, and then we see the explosion itself, but it's very rare that we see both. Kind of, the mugshot and the explosion itself. What we usually see is, explosions over large distances, especially when they're luminous, you see them over large distances, and we want to map the stars to the explosions. And we've been observing a lot of kind of a zoo of different kinds of stars, and Marc will mention that in a second in detail. And we're also observing a zoo of explosions. And so we want to match them, and that impacts many fields, impacts cosmology, understanding what the progenitors of 1As are, type 1As are. It's still an outstanding question. We think they're white dwarf explosions, but that's perhaps a certain certain number of them, or they're predominantly, but which subtypes of 1As. And then for GRBs, of course, that's an important question too. What are the progenitors of GRBs? Because that helps us understand nucleosynthesis, it helps us understand, to use them as beacons, to use them as tools. So, so from the spectrum we get subtypes, but the big question is what are their progenitors? So this is kind of the goal of my group. So we have different explosions. We also have the remains, of course, supernova interesting because the remainders or the remains of the explosion, for some cases, are interesting objects like neutron stars and black holes. So in my group, we also study black holes and figure out from which explosion they came and from which stars they came. So this is a big question for many areas. And this is the theme of kind of our group. I call it stellar forensics. We see the death, and we have to work backwards, figure out what star exploded. And that field also, as I mentioned, has been highlighted as a new important field, a kind of time domain, multi-messenger astronomy, and also the decadal survey. Okay. And of course, as always, feel free to ask questions. I know it's a broad audience, right? The astronomers, they're like, oh, I already know this. Others like, oh, interesting. So any question is fine. If you heard anything, if you want to know about Betelgeuse and the dimming, if it went supernova, it did not go supernova. And Massimo, you have a question.
Yes. I remember years ago, I was disappointed because I thought I had a good idea of why type 2A are used as candles.
Type 1A.
Type 1A, sorry. And there was a nice mechanism, and then David Hawke said actually it's not really true, and it's more like fitting a luminosity curve. So
yeah, so Massimo was referring to the fact that for a long time, the reason people saw type 1As from white dwarfs are beautiful beacons in the sense of standard candles, so they have an intrinsic luminosity that's the same, is that we thought they all explode at the same mass, which is called the Chandrasekhar mass, in honor of the American Indian astrophysicist, of 1.4 solar masses. So that was the idea, is that, well, you have, the same kind of star at the same mass that then explodes, and it produces nickel 56, which powers the light. And so you produce the same amount of nickel 56, and so they're standard candles. They produce the same amount of nickel, and therefore the same luminosity. Now that has changed because we first find that lots of white dwarfs in our own Milky Way are not even close to that limit. They're more like 0.6 solar masses, so less by the factor of 2. And then the other thing that's happened is that so it's really hard to imagine that they will actually go to the 1.4. So we think it's kind of a range. And what people think is now it's called standardizable candles. So they're not standard candles, but you can standardize it still by looking at the light curve shape. So that's a whole industry by itself, and a lot of them for JWST. So by the way, all the astronomers on Christmas Day, we're very happy. We watched the launch of JWST, which is a NASA satellite. It was 7:30 in the morning, so we've been awake for like 2 hours already. We watched it, went well. It's kind of, it's amazing. Like it's a big fat telescope in outer space without any kind of enclosure. So it's operating so far. It's been deployed. The secondary mirror has been deployed. It's working. And they found out that the lifetime is actually twice as long as they thought, because the Ariane rocket that launched it was very precise. So it's like a very happy news. So JWST is going to observe the 1As and go to the red wavelength. We can standardize it even better. Of course, for understanding the reason for the acceleration of the universe, it's really dark energy. What's the and then looking at 1As as a function of redshift, I think that's going to be important.
What's the relation between rocket precision and lifetime?
Oh, so the rocket precision comes in because it put it in the exact orbit, and so it needs less thrusters to move it around, because it's going to be sent to what's called the L2, Lagrangian 2 point, and so it's going to be not serviceable, and so it have to be kind of using its thrusters to get there, and so it has to lose, that's my understanding, less of the thrusters, and so it's going to have a longer lifetime.
I think they got the lifetime wrong in that way.
Yeah, not wrong, but they underestimated it because they included more kind of usage of their rockets to actually move it there. Yeah. And the good news, and then if it has problems, we can't fix it like we did Hubble. Right? Hubble has a whole history that it had astigmatism, but then the astronauts would not. But this one would not be serviceable. So hopefully they got everything right. So far so good. Okay, so so now let's talk about supernova subtypes. Get started.
Maryam, I'm sorry, I have another
Sure,
naive question.
No.
So you mentioned the difficulty of this map of, we see the supernovae are rare, so we only observe them when they're far away, and stars are difficult to see that far. But is there any hope that in the near future with new telescopes we can see the star, let's say we could do deep exposures of nearby galaxies enough so that we can hope to see one of them explode? Can we make that map on an
Yes, so
individual
people
level?
are doing that both with Hubble and ground-based telescopes to have maps of all the stars in the nearby galaxies. So we're doing that, but again, it's only, you can only do to a certain distance. And you will ideally want to do it at different environments, including low metallicity, so low metal contact, because it turns out stellar evolution is very interesting at those low metallicities. And so the LMC is an important one. That's where 87A, Supernova 87A occurred. So it's going towards direction, but kind of weird explosions like Grbs. I think we never will see a progenitor of a Grb. Like the closest Grb ever to us was 40 megaparsecs. So I don't think we'll ever see those. So kind of exotic explosions, we won't. The other thing that comes in for kind of the astronomers is that only certain filters are observing these, making these deep exposures, and that mostly in the red, where eyes, also can see. But it turns out for a lot of these stars, we think these are massive stars that are exploding, and they're very blue, they're UV. So we don't have a UV kind of deep exposure catalog, but that would be great. Yeah, massive stars are, hot, black body,
Right.
just basically black body radiation, and so they peak in the UV. So yeah, so that's why it's hard to do. I mean, that's what the direct way, but that's why my group works on kind of this indirect way. And that's where also big numbers come in, so like data science related things. So Marc will talk about that, and I want to finish up soon, and I will finish up with so you has enough time. But that's where also kind of large numbers comes in. Now that we have more transient surveys to kind of make constraints on the progenitor on large data sets and indirect ways. Okay, so what are the subtypes? Very briefly, so we already talked about type 1s, type 2s, and of course there's a type 2b, to be or not to be. Can't help, I have to make that pun. So type 1s don't show hydrogen. And then type 2s do. So of course, hydrogen is the most abundant element in the universe. So it's really surprising to see ones that don't have hydrogen. And the type 1As, right? Those ones, so they don't show hydrogen because they're carbon oxygen white dwarfs. They have lost the outer layers of hydrogen and helium during what's called the planetary nebula phase. So these like barren, cores. And then there are all these kind of 1Ds, 1Cs, broadline 1Cs. So these are connected, the only type of supernova connected with Grbs are the broadline type 1Cs. And so you might wonder, why are these kind of letters mean? So they don't mean anything specific in the sense that just the type Bs don't no hydrogen but helium, and then 1Cs no hydrogen and no helium. As seen in the spectra in obvious ways. And that becomes important because, as we'll discuss, there's a big question about the hidden helium in 1C. So could you have helium? Again, helium is the second most abundant element in the universe. So could you hide helium in certain ways so that it looks like the explosion has no hydrogen and helium in the spectra? And that's important for understanding how you make these 1Cs, how you make broadband 1Cs connection to Grbs, and if they're really helium free, how did you get rid of all that helium? And so the type, and then type 2s have. And so of course that's from spectra, right? Like, kind of after 101, you see the gamma lines of hydrogen, the helium lines are also in the optical wave range, but kind of harder to detect. And so Marc will discuss that. Okay. So the other connection I want to make that's also kind of emergent is superluminous supernova. So as I said, these are kind of 10 to the 10 solar luminosities, but there are subtypes that are even higher, 10 to the 11 solar luminosities. These are called superluminous supernovae. Two superlatives. And so we still debate what they're due to. They also show broad lines in the spectra. So the spectra, even though this is this photometry-based classification, spectra is still important. Okay, so I think I'll end here, and then Marc will continue giving a little kind of intro to spectra, and that's and how we can constrain hidden helium through that. So, Marc, do you want to say what your hobby is?
Yes.
Actually, should do this as a tradition. All the future speakers should say also mention their hobby.
Sure. My name is Marc. I'm a 6th year disembodied brain in Maryam's group of physics. One of my hobbies is chess, both playing and watching the professional scene, which there's a very exciting tournament going on now. Everybody's following the Tata Steel. Yeah, and I guess reading science fiction. I'm going to continue Maryam's very excellent introduction, but I'm going to focus on modeling supernova. And so getting back to your question, but one of the reasons that we want to model supernovae is because there are so few direct detections with pre-explosion imaging. So there's approximately 20 explosion detections. Supernovae, so this is where we have images of the stars before the explosion actually happens, and then we can look at those images and identify the progenitors. These are mostly type 2. Those are the supernovae that have quite a lot of hydrogen in their ejecta, and are the most abundant types of explosions in the universe. I won't really focus on these. So Maryam's group, generally, we focus on stripped envelope supernovae. So these are the explosions of massive stars that have lost some of their outer layers through various processes, either winds or binary companions. And for these stripped envelope supernovae, SESN, there's only about, well, not about, there is only two instances where we have pre-exploding imaging.
Out of curiosity, like, is there controversy, like whether the thing in the image is really the progenitor in these
Yes.
cases, or is it really solid?
Well, so in these two cases, it's pretty solid. I mean, in general, yeah, it can be quite hard to tell, especially, you don't know, because these are the explosions of massive stars. There's also the case of a binary companion that you have to distinguish between. Yeah, I mean, also, it's depending on how far away the host galaxy is, then the images can be, relatively low signal. So yeah, it is generally hard. For these two-stroke envelope supernovae, I think the confidence is pretty high. These two, oh yeah, sorry.
I was just say one last issue with like the pre-explosion imaging on that is all that you really get is a color and a brightness. And for a very late stage stellar evolution, it's actually very difficult to trace like mainstream stellar evolution to the non-LTE processes that happened the last year before they died. So even with like these two filter measurements, you don't know much about them necessarily.
Yeah. And these two that we do have these pre-explosion images for, they're type 1Bs. So these are the ones that have no hydrogen but helium. So in general, the question that we want to answer with modeling is how do we explain the observed spectral diversity? And there are a bunch of factors that impact this diversity. So one is the types of stars that explode. By this, I mean the masses. Mass, of course, is one of basically the most important property of a star that defines how it will evolve over the course of its life. And also the composition of the star, so what elements are present. There's also the environment of the star. So specifically whether the star has a binary companion or a single star. This affects the different types of mass loss pathways that can go on over the course of the lifetime. So when you have a binary, you can have interactions between the two stars and mass transfer. And then there are also explosion characteristics. So things like, is there a jet, the explosion energy, asymmetries, that sort of thing. So all of these pathways kind of contribute towards the observed diversity in supernova spectra. And the goal of modeling is to try to connect properties of the models, like the masses and the composition of the stars, to actual observed properties of the spectrum. So there are a few important challenges that I want to highlight before I get into the details of supernova modeling. So as you can kind of see from the contributors towards the spectral diversity, this is a really complex process. So first, you need to have some sort of realistic progenitor model. These come from stellar evolution codes. So something like MESA, this is the most popular one. So these codes will handle taking a star from the main sequence and evolving it over the course of its lifetime. So this is a very long time scale up until the point where it would explode. Then you need to also have a realistic explosion. This type of code, so this is an example of a code that does this called Flash. Realistic explosions are quite complicated because you require, they happen on extremely fast timescales, less than a second. And there's a very large kind of dynamic range in all of the parameters that you have to track like the density, and distance from the center of the star, that sort of thing. So this is quite complicated. These explosion codes generally can only model, up to around a second after the collapse. And there are many ways of doing this. Some, the most kind of realistic ones, incorporate the feedback from neutrinos so that you're getting an actual physical explosion. But most codes simply kind of inject energy or force some sort of bounce to happen in the core so that the star will just be artificially exploded.
These are like three-dimensional models.
For the most part, no. I mean, yeah, there are some groups that do three-dimensional simulations of the explosion. That's really complicated, and there's only a handful of those models that are available that have ever been run. Flash lets you do it in one dimension, so there are people working on doing 1D explosions, but then calibrating those with extra parameters to the handful of 3D simulations that have been done. So those calibrated 1D explosions are pretty good. Basically you want you want the codes to agree on a star of mass M to explode versus have a failed explosion. And so for the most part, there's agreement when you use these calibrated 1D models. But yeah, I mean, as computation power gets better and things like machine learning is incorporated directly into these simulations, it may be possible to have more and more 3D simulations. Finally, there's Rad Transfer. So this is after the explosion. This is the modeling that I do, and the code that I use is called TARDIS. This is an open source 1D time-independent radiative transfer code. With
Glennis is raising her hand on Zoom. Glennis, do you want to talk? I think that we should be able to hear you.
I just was going to ask is what, and I assume magnetic fields aren't included. That could be really interesting, in fact.
In which one of
Well,
these?
for example, in Flash.
In Flash, I assume they have some way of incorporating the magnetic fields. I've never actually used Flash, so I can't say for certain. But yeah, I mean, we don't take that into account for the radiative transfer.
Yeah, some of the kind of GRB explosion models include MRI, magnetorotational stability, that comes from magnetic fields.
Yeah.
And it seems like that's important for making the jet.
Yes, that's true. Okay, so yeah, I'm gonna now kind of zoom in on the radiative transfer part. Because this is the type of modeling that I focus on. And the goal of radiative transfer is to go from an observed spectrum and try to understand properties of the progenitor through reconstructing the ejecta of the exploded star. So just a kind of quick aside on spectra. So the spectrum that we look at kind of looks like this. It's basically just a combination of a black body, which is emitted from the photosphere, plus P Cygni profiles. So these are, we have something that looks like a black body. And then on top of that, you'll have a P Cygni profile where this is 0 kilometers per second. And this is some absorption velocity. It's usually around 10,000 kilometers per second. The reason the emission peak happens at 0 is because if you look at the model of what is happening, so here you have a neutron star / black hole that is formed. Here's the ejecta. Photosphere. This is from where the black body is emitted. Inside here, you have a very high optical depth, so you don't see anything that's happening inside the photosphere. Outside the photosphere, you have a low optical depth. And so, there's an emission region. Here's your eye. There's an emission region that is approximately symmetric with regards to everything over here is blue shifted because it's coming towards us. Everything over here is red shifted because it's moving away from us. So with regards to the emission is all approximately symmetric, but with regards to the absorption, this region is occulted, so you don't see any absorption from here because the photons are not reaching you. And so you overall get a blue shift. So yeah, this is approximately the, what the data looks like that we're trying to recreate with our modeling. And this is exactly the sort of structure of the model that TARDIS assumes. So TARDIS approximates this photosphere at a fixed location, not actually in real life at a fixed location, because the photosphere is going to be wavelength dependent. But it's a pretty good approximation. And TARDIS works by propagating photons through the ejecta and simulating the atomic interactions between the elements located in the ejecta and the photon packets. Are there any questions? So as Maryam alluded to, the specific question that I'm interested in answering is there helium in the ejecta? And in particular for these types, type 1c supernovae. In general, radiative transfer modeling of supernova spectra is quite complicated. So it's much easier for just rad transfer for stars, but when the star has exploded, you get very high velocities. So this causes the lines to broaden. You also get line blending, depending on when you're modeling, because the photosphere will recede and over time and reveal lower velocity material. So you have a combination of high velocity material producing very blue shifted lines and also low velocity material using lesser shifted lines. And they can combine and merge and make it very difficult to look at a spectrum and say, if you see a little dip here, attribute it to one element. You really can't do that. There are line identification codes that kind of help with that sort of process, but in order to really constrain the abundance of elements in the ejecta, you have to do a full radiative transfer model because all of these lines are blended to some extent. For helium in particular, so, we see, as I won't erase Zoom instructions. So where's helium? For type 1c supernovae, we have observed spectra that seem to lack both hydrogen and helium absorption features. And so the immediate question is, does this mean that the ejecta actually lacks these elements? And if so, how is that possible? Because these are the explosions of massive stars that we know are composed primarily of hydrogen and helium. Hydrogen generally lives in the outermost layer. So here's the core, the inner layers, and then there's the outer layers where you have lighter elements like hydrogen and helium. It's relatively easy to get rid of hydrogen. because it's the least gravitationally bound layer of the star. But helium's much more difficult. So, for example, getting rid of helium. So how to get rid of helium? It requires generally one of two things. A really massive progenitor, like a Wolf-Rayet star. These massive stars have very high winds, and so they blow off over the course of their lifetime, the majority of the helium. Or you need a binary. And this binary companion will, through Roche overflow, take off the outer layers of the primary star that explodes and gives rise to a type 1c supernova. You can just, through an analysis of supernova rates, actually deduce that massive single stars cannot be responsible for all of the type 1c supernovae that we've observed. Because of course, these require the most massive stars. Those are also the rarest stars. So we know it has to be a combination of these two progenitor pathways. And then a natural follow-up question is, how many binaries contribute to 1Cs versus the single stars? And is there actually a difference between the observed spectra that we see from these two pathways? So, the 1C category makes it sound like, oh, it's like the 1As, everything is quite standard. But it's really not. A lot of these stripped envelope supernova categories, the 1Cs, the 1Bs, the broadline 1Cs, 2Bs, there's quite a lot of diversity within those groups. So there are 1Cs that have very blue featureless early spectra, and there are 1Cs that don't. And so, it's possible that this difference in progenitor pathway can explain some of the diversity within this 1C category. But there, oh yes.
Stars can also burn helium, right? So there's no way to get rid of enough helium just through helium burning?
So especially in the case of high rotation, there's the possibility that you can have flows from the outer layers of the star into the center that will burn off all of the helium in the outer layers. That is true.
So that's, I think, hydrogen, right?
It is hydrogen. It has also, though, been positive for helium, but it can't be responsible for burning all of the helium. That is, it's a less likely pathway. From the simulations, people don't think that you can get rid of enough helium to produce something that looks like a 1C spectrum. So there is a complication, though, which Maryam hinted at, called hidden helium. So helium is special in that the lines that we observe are formed through non-thermal excitation. So the powering source of these explosions is the decay chain from nickel-56 that's produced. And so those decays produce gamma rays, and those gamma rays, through content scattering, will accelerate electrons. And so there will be some population of non-thermalized electrons that can excite helium and produce these helium. So it's been posited that if you have a supernova ejecta like this with very low nickel mixing, so that is, the majority of the nickel is located deeper in the ejecta of the explosion, whereas the helium is all located in the outermost layers, but it's possible that you could have invisible helium, which is just the helium hasn't been non-thermally excited yet. So this complicates everything because it means that you could have helium present, and it just won't make any imprint on the spectra that you observe. So it's really important to be able to constrain the amount of helium through radiative transfer simulations. First, to say, given some model, can it hide helium in it? And if it can't, then how do we explain how the helium was stripped off of the projector in the first place? So this is kind of the topic of one of my papers where I studied a particular 1C SN 1994I. Essentially, what we did in this paper was to start with a well-motivated hydrodynamical simulation of a progenitor with the ensuing explosion for this event, and then do a systematic search, inserting more and more helium mass into the outer layers of the ejecta, and using this radiative transfer code TARDIS to look at what the synthetic spectra looked like. And we found that when we inserted a very small amount of helium, the low helium produced visible lines that were not present in the observations. And so through this process, we come up with an upper bound on how much helium could be present in the ejecta of this particular supernova. That upper bound was about 0.05 solar masses of helium, which is very low. So the kind of progenitor stars of these explosions can have up to 1 or 1.5 solar masses of helium in them. So at least for 1994I, we're quite confident that this is truly a helium poor explosion, and combined with
When
this.
you add helium and see what happens, that's in the radiative transfer code, or which?
Yeah, so we have models where we inject more and more helium and then produce synthetic spectra with radiative transfer. And so the radiative transfer shows that even with small amounts of helium in the outermost layers, the spectra that are produced have absorption features, which are not matched by the observed data for 1995. Yeah, so combined with the low ejecta mass for this event, we're pretty certain that this 1C comes from a binary progenitor. Now, this is just for one supernova, and much as I would like to spend the rest of my life modeling all of the other 1C supernovae in exactly the same way, I think I would get bored. So I'm not doing that. One of the challenges of supernova modeling in general is that the codes are computationally very expensive. Particularly if you're going to do something in 3 dimensions. TARDIS is a 1D code. So of all of the available radiative transfer codes, TARDIS is actually quite fast. It's basically the fastest code. You sacrifice some things in terms of assumptions, like we don't have time dependence. But yes, it is one of the fastest codes available.
Sorry, just a quick question. What do you mean by fast? So how long do you run one simulation? Is it days, months, weeks?
TARDIS can simulate one of these models in a matter of like 10 minutes.
Oh, wow.
Yeah, whereas, if you use a full 3D time-dependent code, it can take millions of CPU hours.
What do you mean you don't have time to fit it?
So TARDIS assume we make this synthetic spectrum at a fixed snapshot in time. So you assume there's a fixed snapshot and then propagate photon packets through and then converge to a steady state solution. Right, so even with TARDIS, in order to do some sort of, the ideal is have some way of fitting models to data. This previous work that I did on 1994I required having an understanding of the type of progenitor, picking a good model, and then developing this systematic method for inserting helium. Generally, people who want to model supernovae spectra just have to do this by hand. And that's very difficult if you're using an expensive code. It's still difficult if you're using a fast code like TARDIS. It requires a lot of expertise. So really what you want to be able to do is fit models to data, and that's currently what I'm working on. And I don't know if I'll have time to talk about it in detail, maybe just for a couple of minutes. We're achieving this through the use of a machine learning technique called emulators. And basically what an emulator is it's an interpolator. So we start with some set of priors. These are things like the elements in the ejecta and the density profile of the ejecta. So with priors over all of these parameters, you can create a grid. of course, this is usually around 15-dimensional. For the simplest model, it can go up to hundreds of dimensions if you want to have a really complicated model of the ejecta. So imagine this grid is 15-dimensional, and you can produce synthetic spectra with TARDIS for this grid. So you'll have some spectrum for each one of these grid points. And what the emulator does, it is really, it's just an interpolator. So you want to be able to sample some random point from your prior space and say, given this set of sampled parameter values, what does the synthetic spectrum look like? And then you can compare it to data. It's totally infeasible to pick this sampled point and then run a full simulation, even with a fast code, because the number of points that you would have to sample just to fit one model to one, to fit models to one observed spectrum could be in the millions. So you have to have an interpolator. I mean, this is a strategy that people constantly use in physics. The fact that the interpolator, is approximating a function. TARDIS is just a function. It goes from a set of input parameters to a spectrum, very complicated function. And so you cannot approximate that function with like a polynomial, right? Which makes sense. So instead, we use a neural network, which is a very flexible, nonlinear function approximator. And so this gives you some interpolator between grid points. And you use that interpolator to do inference. Basically, you pick a point in this parameter space, ask the interpolator what the spectrum looks like. The interpolator will tell you, and you have to, of course, characterize the uncertainty. And then you can compare that sampled point to data, and that comparison uses a likelihood function. And then you just do this process millions of times, and eventually you will come up with some fit of your model to data. And so this will give you posterior distributions over all of the input parameters, which would include helium abundance, for example. So this is the sort of thing that I'm currently working on. The goal is to use this sort of methodology to not only fit models to individual supernovae like 1994I, but the entire class of 1Cs, so that we can look at the diversity of models and compare it to the diversity of observations. So I think with that, I will stop. Okay. Well, it's 1:30, so lunchtime.
So how many parameters? You said 15?
Yes, 15. So generally, like,
You don't really constrain all of it, or is it like?
yes, yeah, you can constrain all of them. That will assume a very simple model of the ejecta, so uniform abundances within the entire ejecta, which is of course not true. But this is no one has really ever done this work before, so we're starting from kind of the simplest assumptions. And it's quite good if you are smart about like when you do the modeling in terms of the evolution of the supernova. So if you do it early in the lifetime of the supernova, then you're looking at the very outermost layers. And so that kind of the difference between the outermost layers versus the innermost layers is less apparent. But if you wanted a very complicated model with different values for those elemental abundances in multiple shells, yeah, it can easily get up to 100 dimensions, and nobody's ever done that before. So that's a very long-term goal of this methodology, and we'll see if it's possible.
Can I ask a question from Zoom? I can't quite see the room, sorry. I was just curious, it's a sort of maybe silly question, but what you were describing the input is like a grid in 15 dimensions.
Yeah.
Actually a grid, or you just like uniformly sample it?
It depends on the parameter. So for for the elemental abundances, we try to be informed by hydro simulations of progenitor models and look at, I think we do log uniform sampling for the elemental abundances, and then things like the velocity and temperature of the photosphere. Those are uniformly sampled, given reasonable bounds from our experience. So yeah, it's not a perfect evenly distributed grid.
Okay. Thank you. Yeah, I guess I could say that there are some kind of interesting things we've been playing around in sort of LHC context where we also have higher dimensional parameter spaces and computing as an issue, where we try to be sort of, you do some kind of, I guess, of the inference, and then you run more simulations, but you run them kind of in the right spots,
Yeah.
And there's some kind of like iterative loop there, which could be maybe interesting in your setup as well.
Yeah, we should talk about that more. Yeah, I think that could be quite helpful.
A sociological question.
Yes.
Like this, building models of supernovas seems theoretical, although you compare them to data, but like they're I think of you guys as observers, or
Yeah, but Marc came.
Don't
with his
lump me
views
in there.
apart.
I don't know how a
Yeah,
telescope
maybe I
works, and I have no interest.
So yeah, no, we do. So his co-advisor is Wolfgang Katzler, who's a co-writer and Doctor Who lover. He came up with TARDIS. So yeah, so we've been co-advised. So it's been actually really fun because with Wolfgang they can do the kind of computational aspects, and then we can talk about kind of the observations. So it's actually
something
really
really
cool.
at the interface.
Yeah, it's both interface. Wolfgang was a postdoc here before. He moved on as a faculty there at MSU, so it's been working really well.
Okay. More questions? Stay. Marc and Maryam. Perfect. Yeah.